So let's get started with the Edison model first, and then we'll do the Tesla model in the next video. For this one, if you'd like to try it yourself, pause the video now, try it out, and then we'll check the answers together. If you think it is too difficult, you can pause anytime you like, or the worst case is you can simply follow with me that to do this whole page, and then for Tesla model, then you should be able to do it by yourself. Okay, so if you want to pause video, you can pause it now. So first of all, in the question, this is a very simple model of how Edison's proposed in the documentary. So apparently there's a power station, and there are transmission cables simply connects from power station to the building where the demand of the electricity is needed, and it is supplied at this voltage and also this power. Okay, so one thing that you need to bear in mind is the long transmission cable has a high resistance. So here, let's make it as 1000, and so let's try to do some calculation here. So it should be quite straightforward, and you should be able to do it actually with the knowledge in the previous chapter. So first of all, it asks you to calculate the current flow through the cables. Reminded that this is 1000 ohm, and the lower one is also 1000 ohm. Oh, actually no, sorry, it's total resistance. So both of them altogether is 1000. So maybe you can say 500 500. It actually doesn't matter. So say 500 and 500. And current flow through the cable. So in fact, you don't have to care about the resistance yet, because you already find if this is the result, then how much current you need to be. So you got power, you got volts, then think about what equation you need to use. P equals to VI. So we have power, which is 2000, voltage is 220, I is the unknown, and therefore I will be using your calculator equals to 9.098. Okay, so this is the question answer for first part. Part 2 is asking you to calculate the power loss. Since if you remember in the previous video, we talked about when you calculate power loss, I would encourage you to better use I square out instead of the other two. The thing is, once again, voltage here is referring to the potential drop, which you cannot tell easily from here. So it would be the best if you could simply do I square out here. So let's try to do it. P equals to I square out equals to I, which is given from the previous part, and then the R is in a total of 1000, because we are talking about in the cable, right? So 1000 will be the total. So here we get, if I use a whole number from the previous question, I will get 82644.6. So round it to say 826 maybe watt. Okay, if you like to use a scientific notation, that's fine too. We can do 8.26 10 to the power 4. Voltage drop across the cable. So this is where it gets to explain why we didn't use voltage, that equation for power, like V square over R or IV, because voltage you have to calculate it, and that will be more steps you need to do. So in order to calculate voltage drop simply, you can use V equals to IR. And so for V across the both cables, right? Both cables, then we want to use the current, which is 9.09 from part 1. R is 1000, and therefore the voltage drop is 9090, and that will be the voltage drop. Then you may ask, hey, so how could we have 220 volts here, right? And this is actually the next question, right, that we are asking you. Think about this. We never mentioned how much voltage is produced by the power station and how much power is produced by the power station, but that we already know across the cable it is 90 2.90 volt wasted. It's literally wasted because it's spent on the cables as heat. And only 220 volts is actually dropped in the household building. So think about what you need to have at the beginning. Imagine this is the battery for the power station. Then what you need to have for the actual voltage for the power station will be, or input I should say, maybe input will be 9090 plus the actual useful one, which is 9310V. And so for the power, it will be the same, because the same way to do, because apparently the total power, you just have to calculate the power in the cable and the power in the building. And in fact, power in the cable you already calculated in part 2, which is 82600, and for the building is already given, which is 2000. And so you just add them together, so 84600 watts will be the answer. So finally, it asks you to calculate the efficiency of the whole transmission system. Once again, if you calculate efficiency, you should be using the equation of useful output. It could be energy, it could be power, that's fine, versus the total, or simply just input, times 100%. So right here, what we have for actual output is 2000 in the building, and the input is the one that you calculated, so 84600. If you try to calculate this, you will find it is, of course, I mean, if without calculation, you should already know. The efficiency is only 2%. Okay, so that means if you try to quantify the whole idea of the energy in terms of money, let's say you have to pay $1,000 this month. The actual money that, I mean, used on whatever you use at home, those electrical appliances, is only 2.36%, which actually means it's $23, right? It's actually being used like properly on your home, or you can think from the energy perspective as well. It's a waste of energy also, and that, of course, that would further worsen the global warming situation. While the rest of them, which is the rest of $977, are simply wasted across the cable. So of course, it's not really the Tesla's idea is brilliant, but also you can see Edison's model is really not feasible. But of course, I mean, how he wanted to do is he didn't actually care about the science behind. I mean, it still work, but then in terms of commercially, what he was thinking probably is it doesn't really matter whether it's efficient as long as he can charge people for more money, right? Whenever people find it's useful, they will just pay for it. Just like sometimes when people want some luxury car or anything, some technology stuff, they just want to pay for it. They don't really care about whether the money was well spent or not. I think this was the mindset that Edison were having. But as you could see from the documentary, they also said because of the design has a fundamental problem, they can only build the transmission cable from the station by only around 2 km, if I remember correctly. And then from each of them, then they have to build like another station to kind of continue the power supply. So then imagine if you have a very far away distance from the power station, you can see there's a lot of station between you and the actual power station, which is ridiculous. Okay, now I think it's a time for you to try the Tesla model, and be careful. One thing is that when we want to make it fair, although we are not doing experiment, but we still want to treat them fairly. So what you can see here is with the same scenario where at the end, we still want to produce the same amounts of power with the same voltage, while in the middle for transmission, we still have the cable which has 1000 ohm resistance. So the whole thing is perfectly fair. The only different thing is we have added two transformers here. One is stepping up, one is stepping down apparently. So pause the video now, try it out, and yes, we have to assume the transformer has to be ideal in our case first. Okay, so pause the video, try it first. Okay, so let's take a look of part 1. Part 1 is asking you the current flowing through the cable. Although I know it's AC, but let's just draw it so that you all can illustrate and have a better idea visually. So before we calculate I, we actually have to calculate something else first, because there's no way we can calculate I directly. The first thing that we have to calculate before this answer is to calculate the current within the secondary coil, which means on the building side. Actually, we have already calculated this one. Let's just give them some number. How about that? If I call this I1 and I2, this is I2, and then I'll call this I3. Okay, so I3, which is the one again circulating in the building, is already calculated in the previous page. So let's just take the number, which is 9.09. Okay, and then you can start to see the relationship that between I2 and I3 as you learn the equation from the previous video or the textbook. Then you can see that they have the relationship with the number of turns as well, right? This is the equation that we talked about last time. So by using that, you can simply devise the equation that they are in the inverse proportion. So I2 over I3 would equals to n over n, and then think carefully which n over which n. It has to be the opposite one. Again, if you don't know why it's opposite ratio, go back to the previous video and I have explained about that. Okay, so since we already know the number of turns 800 to 1 here, then we can substitute here. So this side 1, this side is 800, and then for I2 is the one that we want to find. I3 is 9.09. So through that, we can find the current in the cables, which is actually 9.01 divide 800, which is 0.0113625. Okay, let maybe just write it up to 0.0114 then. Okay, the unit is 8. And just double check one more thing is that does it make sense? This actually is sensible because if you remember from the previous video, we said that for the Tesla model, we are trying to lower the currents within the power transmission. And yeah, this is what it is, right? Lower the current so that power loss hopefully is less. Next up, the power loss in the cable, right? So again, we'll use the equation of P equals to I squared R, while I is the one that we find out 0.0. Let's just use the whole number. How about that? And R is 1000. Again, the whole set of cable is 1000. And so again, go with your calculator. Then you find, surprisingly, the power loss in the cable is only 0.129 watts. In fact, the victory has been shown, right, already. If you try to think about the power loss in the cable in the Tesla case, which is 0.1, how about just give it as 1 watt, even if you like so. But in Thomas Edison case, you can see it's enormously large. It's 2600 watts. So you can already see like who's the winner here. But anyway, let's continue with the rest of the calculation. In fact, the question also asks you to calculate the voltage drop. So the way to do it is similar to the Thomas Edison's model, which is V equals to IR, and V is the unknown, I is the one that we have, 0.0114, or you can use the whole number if you want, and 1000. So that should be, I'm just checking with my calculator in case I make any stupid mistake, 11.4 volts. So in other words, you will have that much of voltage drop here. Next question may be a bit tricky, so let's try to do it together. And let me just reiterate to you, here the building will take 220 volts, and the cable itself will take 11.4 V. Okay, and so what is the voltage in the power station? So first of all, think about that. When the voltage is converted between in this transformer, so it was something and then converted to 220, what would that be? Alright, and we can use the equation of V. Let's just call 2 is the one in the middle, 3 is the one near the building. Then again, the ratio will be the same as the transformer, which is 2 is the one that we want to calculate. V3 is 220, and then the ratio is number of turn, 1 to 800. And so the V2 is 220 divide 800, yeah. So wait, it doesn't make sense. Did I do anything wrong? Oh, actually, sorry, I make a mistake here. It's not 1 over 800 divide 1 here, sorry. So yeah, because it should be high voltage, right? It doesn't make sense if it is low voltage. So keeping yourself in mind about what should be high, what should be low, actually helps you to avoid some careless mistakes also. So that will be the voltage that you would have before converting the voltage to 220 at this side of the transformer. However, since 11.4 is already dropped before the conversion, then on this side, you can imagine, maybe I make clear this up. Here you have 176000. Then here, then you should have a bit more because that is the 11.4 that got reduced. So this side, I would say it is 1760 11.4 V, which you may find is almost like nothing changed, right? And this is the nature of the Tesla model here. Okay, so if you really want to answer it, then this will be the answer, 176011.4 volt. As in for the power, then it's easier to calculate. It's simply, once again, the total power. Since within the transformer there's no energy loss, no power loss, then the power is simply the one in the building and the one lost in the cable. So 2000 from the building, and this one 0.129 in the cable. So that is simply almost the same as 2000. Finally, let's calculate the efficiency, and of course we know it will be extremely high because the actual useful power, I'm not going to write the equation again, so simply the useful power is 2000, which is the one in the building, and the one you actually had to spend initially, input initially, is 2000.129. So if you try to really use your calculator, I actually bet it's very close to 100%. So, well, actually, yes, you will find it's 99.99355%. Let's just call it nearly 100. Okay, so this is why, again, if you watch the documentary, the investor actually decided to go with the Tesla model because they are simply convinced and driven by the economical reasons. Alright, unfortunately, at the end, it's not only about science, but also about how the world works, that is driven by economy, right? The money itself, the business itself. So those investors, those bankers simply would agree with Tesla and then go with his model. And unfortunately, Tesla was simply really a good guy. He did not have any patent on the design, and therefore he did not actually earn a big fortune out of it, because he simply want to share the idea and also the design so that more people can be benefit from it. And therefore he, at the late life of Tesla, he wasn't very happy, because he's almost like getting abused by other people, business people, and he got depression, as I remember. If you want to know more about his story, go and try to Google it. Alright, it's quite sad. But again, we should pay more respect to such a great scientist, inventor. Without him, our technology and our life would not be as high quality as we have nowadays.